This video, we're going to start talking about polar coordinates out of section 8.3 in our book. So we have learned in your past math experience how to plot points using what are called rectangular or sometimes Cartesian coordinates. So these are what are our familiar x and y coordinates. So we know from what you've done in the past that every point in the plane has a location, kind of an address, where you go, at whatever the x coordinate is in the horizontal direction and whatever the y coordinate is in the vertical direction, and that takes you to a particular point. And that's unique. So the point 3,4 identifies a single point in the plane, and that's the only coordinates for that point is 3, 4. And -2, -1 would be in a different place. And so every point in the plane has a unique set of x and y coordinates, and every number x and y represents a point in the plane. But there's another way of doing this, and that's called polar coordinates. So our xy axis, which we're familiar with, we give a little bit different names. So the positive x-axis will be referred to as the polar axis, and the origin, where 0, 0 is called the pole in polar coordinates, although we'll kind of flow back and forth between the two of them. So it's not a huge deal which one you use, but don't be confused with how it's presented to you. So if we're talking about a particular point in the plane, we can think of as starting at 0, and the angle theta may be in either radians or degrees. It'll just vary from one problem to the next, and that's hopefully not going to be confusing. You can identify the degrees when you see the bubble, and you'll know if it doesn't have the little bubble, then it must be in radians. So a positive angle, like we've done in trig, means we are going to go counterclockwise through that angle. And then whenever we've gone through that angle, that designated angle, then we come out from the pole a distance of r, and then that will identify where we are in the plane. So the theta is the angle that we swept through, and theta can be positive or negative, and r is that distance from the pole, and surprisingly enough, r can be positive or negative as well. In a moment, we'll talk about the significance of a negative r. That can be a little confusing at first. It'll also be a little bit different in that we'll explore this a little bit more in a moment, that whereas rectangular coordinates are unique, that if we have the point, say, 2, 5, that's the only way to identify where that point is. And we'll see that polar coordinates are not unique. But let's cross that bridge here in a moment. So let's practice just plotting some points so we kind of get the idea of what this looks like. So to plot the point P, we want to think of going to the angle pi over 3, which is going to be somewhere along here. And then we want to come out from the pole a distance of 2, and we're free to set, whatever length we want to be 1, the scaling. So I'm just going to arbitrarily say there's 1, there's 2, and so that point right there is going to be our point P. It's a distance of 2 from the pole along the angle pi over 3. Now, to look at Q, we see we have a negative r. So first, let's go to the angle 3 pi over 4. So remember, we're going counterclockwise. So 3/4 pi is going to be out here in quadrant 2. So there is going to be 3 pi over 4. Now, we're going to go a negative. A negative r value means we're going to shoot back through the pole that length of 1. So that's going to actually put us into quadrant 4. So here's our angle, 3 pi over 4. The negative r means we go back through the pole to the point Q. And r, we're going to go a negative 45 degrees, so that's going to put us right in the same place we were with negative r value for q at the angle 3 pi over 4, but now we're going to go a length of 3 out from there, and that's going to put r on the same angle as q, but a longer distance from the pole. Okay, now let's look at this idea that these are not unique. So let's consider some other possible representations for the point P. Remember, P is over here in quadrant 1, and it is a length of 2 from the pole at an angle of pi over 3. Well, one thing we could do is we could, instead of getting to this pi over 3 this way, we could run our angle going negative. We could come around this way. And so that would be an angle of, let's see, 2 pi minus pi over 3, 6/3 minus 1/3 is 5/3. So that would be a negative 5 pi over 3, and the r value would still be 2. That also would put us at point P. Now, we could also, and here's where it gets kind of crazy, if we shoot this angle down through here, now our reference angle here is still going to be that pi over 3. So if we come around, there's pi, which is 3/3, plus another reference angle of pi over 3. That angle is going to be 4 pi over 3. That's putting us into quadrant 3. And then if we shot through the pole a length of negative 2, that would put us at that same point P. So an r value of negative 2 and an angle of 4 pi over 3 would also work for point P. We could also go through a negative angle this way, getting to that same place. So remember, our reference angle here is still pi over 3. So that's 3/3 minus 1/3 is 2/3. We're going in the negative direction, so that's going to be a negative 2 pi over 3. And the r value there would need to be negative 2 as well. And we could still go, more than just 2 pi. So we could go all the way around the circle. There's 2 pi, and continue another pi over 3. So that would be 2 pi over 3 is 6/3 plus another 1/3 would make that 7 pi over 3, comma 2, and that also would take us to P, and so on. So there's an infinite number of representations there, which can be a little disconcerting when you get started. Okay, so let's talk about coordinate conversion. So we're going to go back to our graph where here's our generic point P. I put it in quadrant 1, but it can be anywhere. And you can see the polar representation in the green, where r is that distance from the pole, and theta is that angle that sweeps from the polar axis or the positive x-axis. And x and y are our standard representations of the horizontal and vertical distance from the origin, and they make up the sides of our triangle. So if we knew the x's and y's, then we could find r by just using the Pythagorean theorem and getting the square root of x squared plus y squared. If we knew the x and the y and we needed to know the theta, we could use our relationship. The tangent theta is opposite over adjacent, and then take the inverse tangent of that y over x. Now, here you're going to have to be a little careful and make sure that the theta you use is going to put you in the correct quadrant according to what the x and y values are. That if they're both negative, that's going to have to be an angle that's in quadrant 3, where x and y are both negative, and so on. So you can't just blindly take the inverse tangent without considering that you may be really just getting a reference angle, and you're going to have to actually carefully choose the correct quadrant that should be in and adjust the theta accordingly. And likewise, if we know the r and the theta, then we can find x and y using the relationship that comes from cosine theta is adjacent over hypotenuse. Therefore, multiplying the r over gives us x is equal to r cosine theta. And similarly, since sine theta is opposite over hypotenuse, we get that y is equal to r sine theta. All right, let's see if we can do some of these. So if we want to change from the polar coordinates for 7 pi over 6, then we are going to recognize that hopefully x is going to be r, which is 4, cosine of 7 pi over 6, and y is going to be 4 sine of 7 pi over 6. Sometimes this may require a calculator, sometimes I won't let you use a calculator, and these two are known values, so I would expect you to get the exact value, that is, don't use your calculator. So if you remember 7 pi over 6, there's 6 plus 1 more sixth, is going to put us into quadrant 3. Our reference angle is going to be pi over 6. Cosine starts big, so cosine at 0 is 1. At pi over 6 is going to be square root of 3 over 2. So that's going to be 4 times. It's going to be a square root of 3 over 2. But then because we're in quadrant 3, both sine and cosine are negative. The x and y values are negative. So that's going to be a negative square root of 3 over 2. We can cancel those, and so our x-coordinate is going to be a negative 2 square root of 3. Similarly, at 7 pi over 6, again, our reference angle is pi over 6. Sine starts small. Sine of 0 is 0. Sine of pi over 6 is 1/2. But because we're in quadrant 3, sine is negative there, so that will be a negative 1/2. And we'll end up with a y-coordinate of negative 2. And so our rectangular or Cartesian coordinates are going to be a negative 2 square root of 3, comma, negative 2. Now the next one, we can see that we are in degrees for a q. We still are going to do the same thing. The x value is going to be 2 cosine of a negative 200 degrees, and the y will be 2 times sine of negative 200 degrees. This is not a known value, so here we can just enter it into our calculator, make sure you're in degree mode, and it'll be just punching that into cosine negative 200, and I believe that's going to give you an x value of negative 1.879. And when you do that for the sine rather, I believe you're going to get a positive 0.684. So we need to be able to use radians or degrees and non-calculator and calculator problems both. Okay, let's go the other way. Now we're going to start with polar or rectangular coordinates or Cartesian coordinates, negative 2, 2, and we want to convert those into polar. So we can, sometimes we need to know for the angle anyway, which quadrant we're in. So a negative 2, positive 2 is going to put us here into quadrant 2. So that's going to be negative 2, and that's going to be 2. So the r is just Pythagorean. That's going to be the square root of negative 2 squared plus 2 squared. So that's going to be 4 plus 4. That's going to be the square root of 8, which is 2 square root of 2. Now the theta, we can do this one without a calculator. This is actually a known value. We can kind of, I think if you kind of look at it, you can see that this angle is going to be 45 degrees or pi over 4, which is going to make this angle be either 135 degrees or 3 pi over 4. I'm going to use the radians, so I'm going to call that 3 pi over 4. So our coordinates, our polar coordinates, are going to be 2 square root of 2, comma, 3 pi over 4. Okay, and those are not unique, and we'll explore that more in the next one. So for the second one, now we have, here are going to be our rectangular coordinates or Cartesian coordinates, and we want to come up with 4 different ordered pairs in polar form, and the theta is going to go, I think I want that actually to be, I want that to be from negative 2 pi to 2 pi. Okay, so let's see if we can get a picture here. Here's our these are our xy axis. So we're going to be at 2 square root of 3 and negative 2. So we're talking about a point down here in quadrant 4. So this part's going to be 2 square root of 3, and this part is going to be a negative 2. So what I would do here, we can get the r by Pythagorean theorem. So that's going to be the 2 square root of 3 squared plus the negative 2 squared. So square root of 3 times square root of 3 is 3. 2 squared is 4. 3 times 4 is 12. Plus 4 is going to make that the square root of 16. So the r is going to be 4. So now we know that. Now you can do an inverse tangent, but those are always harder to find. Since we just found r anyway, and we can see our triangle, I think it would be easier just to say sine theta, and I'm not going to worry about the negative sign. I'm going to think of that as just being opposite over hypotenuse, which is 1/2. So our reference angle is going to be the angle whose sine is 1/2 is going to be pi over 6. Now, because we are in quadrant 4, we can think of that one of 2 ways. If we go the way I kind of showed it there, that's a negative pi over 6. So that's one possible set of ordered pairs. So we could say 4 comma negative pi over 6. That's one polar representation of that point. Now, we could also get there to that same place by also getting a positive 4, but going around this way with our angle. So that angle is going to be 2 pi back up the pi over 6. So 12/6 minus the 1/6 would be 11 pi over 6. So those are 2 possible sets of ordered pairs that are going to use positive values for r. We can also do this using a negative value for r. So if we extend that angle through the pole out into quadrant 2, remember our reference angle here is pi over 6, so we could say this angle would be 6/6, that's 1 whole pi, minus the 1/6 pi would be 5 pi over 6. That's a positive 5 pi over 6 for that angle. That would put us out here, and then we could shoot back through the pole and get a negative 4 for the r value. That would also take us to that same point B. And we could also, our fourth way of doing this is we can come around to that place over here in quadrant 2 through a negative angle. So that would be a negative 1 1/6 pi, or a negative 7 pi over 6, and then use our negative r value, negative 4, to end up at that same place. And so this is what's going to happen each time. I'll commonly ask you to get to do this, to get 4 different polar representations for a point that's given in rectangular form or Cartesian form. And when I put these restrictions, that I want the angle to go from negative 2 pi to positive 2 pi, which will be typical, then you're going to see you're going to get 2 of those that have positive values of r and 2 of those that have negative values of r. And each of those r values will have 1 positive and 1 negative angle. So that'll be a consistent pattern there. Then we're going to talk about equation conversion, and these are tough because there's kind of an art to it. You don't always do the same thing. So if we're going from polar to rectangular, our goal for rectangulars is to get y equals f of x. That is, can we get y equals and then all the stuff with x's in it on the other side? That's going to happen most of the time, but not 100% of the time. Sometimes we might get something like, say, a circle, where we don't really want to get y by itself because that's not as nice a form. In that case, we'll just stop when we get to something that's recognizable, not necessarily y completely by itself. And as we've seen, sometimes you may not have a y at all. Maybe you get something like a vertical line, x equals 6, in which case it's not going to be in the form y equals f of x because it won't have a y in it at all. So as a general rule, we're trying to get y equals f of x, but we're going to be a little bit flexible, and that's where there's a bit of an art to doing this. Okay, so I'm going to show you here how to convert r equals 4 into rectangular or Cartesian coordinates. Now, there's a couple ways you can do this. There's the standard way. So r, we know, is the square root of x squared plus y squared. So we can replace this r, which is what we want, is to get rid of the r's and thetas and move to x's and y's. And then that's not really where we want to be yet because we don't have y by itself. So we can square both sides, and that will become x squared plus y squared equals 16. Now we could go further and solve for y, but that's not generally what we want to do here because this is a more hopefully recognizable form. If you can see, that's a circle with centered at the origin with radius 4. So we would stop right there. Now on the next one, theta is the inverse tangent of y over x. So we can replace that theta with inverse tangent of y over x. Now we're trying to solve for y, and so to get rid of the inverse tangent, we're going to take the tangent of both sides. So taking the tangent of the inverse tangent, those will cancel. That's f of f inverse. So that's going to get us to just y over x. And the tangent of pi over 4, we're going to have to figure out. This we can do, hopefully, because that's going to be sine pi over 4 over cosine pi over 4. Hopefully we know that those are both square root of 2 over 2, and that makes that equal to 1. So we have y over x equals 1, and we can multiply the x to the other side, and we see that's going to be a straight line, slope 1, y-intercept the origin. Okay? Okay, now a tougher one. Here's where there's a bit of an art to doing this. So we are trying to get rid of r's and thetas, but we know that x is equal to r cosine theta and y is equal to r sine theta. So if we look at this for a moment and scratch our heads, we could see, man, if we could just put an r in there, these would be nice conversions. So the art of doing this is we're going to multiply through by r to insert those r's where we want them. So that will make the left side be r squared. We'll get 2r cosine theta plus 4r sine theta. Now we're making progress. Since we know that r is the square root of x squared plus y squared, r squared is x squared plus y squared. So that left side, the r squared, is going to be just x squared plus y squared. The 2r cosine theta is going to be a 2x, and the 4r sine theta is going to be a 4y. Now at this point, I'd be okay with this if you just stopped right here. If you want to really warm the heart of your math teacher, you might, if you recognized it, be able to get to this. If you subtracted those over and made it equal to 0, then if you wanted to really, really impress your math teacher, you would complete the square in x and y. We haven't really talked about this yet. I don't know if you did this in your Algebra 2 days. We could take half of 2 squared is 1 and add that to both sides. Half of 4 squared is 2 squared is 4 and add that to both sides and write that as x minus 1 squared plus y minus 2 squared is equal to 5. And then you would maybe recognize that that's a circle centered at 1, 2 with a radius of square root of 5. But that would probably cause your math teacher to faint at this point in time. So maybe we'll save that for later. Let's go the other direction, from rectangulars to polars. So now what we see is, I'm going to show you the long way, and then if you've done several dozen of these, as I have, we can do it a little quicker, but you don't have to do it this way. So the x we know is r cosine theta, that's our conversion, and y is going to be r sine theta. So that would be an r cosine theta squared plus an r sine theta squared equals 16. So then we can see that when you have two things being multiplied raised to a power, each of those things that are multiplying each other get raised to that power. So that can become r squared cosine squared theta plus r squared sine squared theta equals 16. If you squint at that and factor out an r squared on the left side, you will see our most famous trig identity, that cosine squared plus sine squared is just 1, and so that becomes r squared is equal to 16, and you could say plus or minus 4, but it won't really matter. You get the same circle, just going in different directions. So r equals 4 would be fine for your answer there. Now the shortcut, like I said, if you've done a few dozen of these, as I have, then you might recognize that because r is the square root of x squared plus y squared, r squared is x squared plus y squared, and see that right away and go right from there to skipping all these steps and saying r squared is 16, therefore r is going to be 4. And it can shorten the process up, but that kind of comes with practice. There's a bit of an art to doing these. Okay, let's try the next one. So here we've got our x's and y's. So let's try making our conversions. Y is r sine theta, and x squared is going to be r cosine theta squared, and we got a 3r cosine theta there. So that's going to be r sine theta equals r squared cosine squared theta plus 3r cosine theta. Let's see what we can do. I think what we want to do here, since we have an r squared, let's get that term by itself first. So we've got the r sine theta, and we'll subtract that r cosine theta to the other side. Let's divide through by the r's, because we can get rid of one of those. So now we have r cosine theta is equal to sine theta minus cosine theta. Then we can divide through by that cosine theta, and we'll get sine theta over cosine theta minus cosine theta over cosine theta. And so r will be sine theta over cosine theta is tangent theta, and then a plus 1. And there's our r is a function of theta. Okay? So, and I didn't mention there, but in general, when we are going from rectangular to polar, this is hard too, because in general, we're trying to get r by itself and theta's all on the other side. But occasionally, like we've seen with the rectangulars, there may not be an r in it at all, and you might just get theta equals like a number, something there. So there's a bit of an art to doing this. We're going to do the beginnings of graphing here, and we'll have some more lessons on polar graphing to come. But kind of the basics is, if r is equal to 3, then this has no theta in it. So that means we want all of the points in the plane that are a distance of r from the pole, and we don't care what the theta is. So that means we are going to, I'm going to be in trouble trying to make this look right, but if we look at all of the points that are a distance of 3 from the pole, and theta is going to run through everything it does. So here, is theta equals 0, theta equals, pi over 6, pi over 4, pi over 3, pi over 2, but r is always going to be the 3. That distance from the pole is always going to be 3. What we get is a circle. So it's a circle of radius 3. That's what the graph of r equals 3 looks like. Now, theta equals pi over 3, if we look at where an angle pi over 3 is, this, because there is no r in it, means r can be anything. So if r is 0, that's going to put us here. R is 1, 2, 5, -1, -2. So what we end up getting is all of the points on that angle pi over 3. And since r can be anything, we get that whole line. So interestingly enough, theta equals an angle in polar graphing is going to be a line through the origin. Now this one's kind of crazy. This is kind of fun to do on our calculator. And when we're in class, we'll maybe do this one. It's kind of hard to do by hand, but if r is equal to theta, then we're going to imagine I'm not going to plot all these points, but you can kind of imagine like a table of values. So when theta is angle 0, r is going to be 0 as well, because they're going to be equal to each other. So on this angle 0, r of 0 puts us right at the pole. So if we went to, like, say, pi over 6, then we know that that's an angle somewhere in here. And we are going to go a length of pi over 6 away from that. So pi being roughly 3.14, it's about 1/2. So that would put us like at a point maybe this far away from the pole. If we did pi over 4, then we know we're at this angle, like at a 45-degree angle, for pi over 4. That's like now 3/4. So that's going to be a little further away than we were at pi over 6. So it's going to do something like that. When we go to, say, pi over 2, now this is like 3/2. We're like at 1.5. For our r value, it's going to be something like in here, and it's going to keep going. So when you connect these, it's going to be this big spiral that keeps going further and further and further away. So it's kind of fun to see on your graphing calculator if you set your window big enough to see that thing going on and on and on. Okay, that's a beginning of polar graphing. We'll look at some other graphs in the next few days.